Hello, good morning. Today I'm here to present our assignment on subject fluid mechanics. Subject code BMMH2313. And I myself, Rajeshwaran Analekina Raja, B0821100420. And my group mate Afzal Hairi bin Abdul Halim, B0821100227. Bernoulli equation. The Bernoulli equation is a fundamental principle in fluid dynamics that relates the pressure, velocity, and elevation of a fluid in a streamline. Theory of our assignment. If the fluid is incompressible, the sum of the pressure, kinetic energy per unit volume, and potential energy per unit volume is constant along a streamline. As the velocity of the fluid increases, the pressure decreases and vice versa, assuming no change in elevation or other external factors. The Bernoulli equation applies to steady and not irrational flow. The Bernoulli equation does not account for losses due to friction, turbulence, or other dissipative processes. In real-world situations, these factors may cause deviation from the ideal behavior predicted by the equation. These are the arguments that we have used in our experiment. A connector, a thick connector, and a hose pipe, and a measuring cup, a hose clip, a stopwatch. A single connector is connected to the holes, and a thick connector is used for create the closed loop, and a hose pipe has been used, and a measuring cup in order to measure the 250 milliliter, and a hose clip for the hose, and a timer. Procedure to water jet height. First, we have to set up the water source along with hose to produce steady water jet, and then we have placed water jet in open area to observe its height, and then determine the reference point from which we can measure the height from the bottom. And measuring tape has been used to measure the vertical distance between the reference point and where the water jet starts. We have to measure the height of the water from the bottom where the water jet starts to the top. Start the stopwatch as soon as the water jet starts. Observe until the water jet reaches its maximum height. Stop the timer as the water jet starts to descend. We have to start our timer once we have opened the water source, and we have to stop the timer once it reaches its maximum height and start to descend. This is how we conduct the experiment. Next is straight line water hose. First, we have to set up the water hose in straight without any bend or loops. Use a lid to close the end of the pipe. Open the water source in order to allow the water flow through the pipe and the holes. Measure the height of the water released from the hole in the straight line water hose. Get stopwatch to measure the time taken to fill the beaker until it reaches 250 milliliter. Repeat the step 4 at each hole in the straight line water hose and measure the height and time taken at each hole. List down all the collected data in the table. First, we have to poke holes in the hose, and then we have to connect the connector in each hole, and make sure we have closed the end of the pipe with a closed lid. And once our pipe is open and the water flow is there, we have to measure the height of each hole, how much the water came out from the hole, and then we have to Measure the time taken to fill up the beaker with 250 milliliter. This is how we conduct the straight line hose experiment. Closed loop water hose. Closed loop water hose method has to be set up in the closed circuit without any leaks. Use the T-connector to close and make the hose into a circle shape in order to create a closed loop water hose. Open the water source, allow the water to flow through each hole. Using measuring tape, record the height of the water that flows through the hole. Start the stopwatch to record the time taken to fill up the beaker until it reaches 250 ml. Repeat step number 4 and 5 at each hole. Measure and collect the data and complete the data table. For the closed loop water hose, we have to use the T connector and make sure it's in the circle shape. And we have used the connector at each hole, and once we open the tap and allow the water source, we have to measure the height of the water that flow through each hole. It has to be done at each hole, and then we have to start the timer and record the time taken to fill up the beaker with 250 milliliter. And we have to repeat all the steps at each hole and make sure there is no leakage since it's the closed loop water hose. This is how we conduct the closed loop water hose. Conclusion. In conclusion, conducting flow rate experiments using open loop and closed loop hose pipes provides valuable insight into fluid dynamics and offers a practical application of the Bernoulli equation. By analyzing the flow rates and applying the principles of Bernoulli equation, researchers can understand the relationship between fluid, velocity, pressure, and elevation. That's all for our assignment presentation. Thank you.
Assalamualaikum warahmatullahi wabarakatuh, and good morning to our lecturer. My name is Afzal Hairi bin Abdul Halim, number metric B0821102227, and today I want to present our assignment task for fluid mechanics. And for the data experiment result for task 1, we collect the data, which is the variable is height of water supply, diameter of pipe, length of pipe, height of water jet, and the time taken. These are the results we got from the experiment. Proceed to the calculation for the task 1. We have to calculate the area of the pipe, the velocity of the water, and the flow rate of the water. So first we calculate the area by using the equation pi r square. So the radius we got from the data is 0.016 over 2, because this 0.016 is the diameter of the pipe, and 0.201 meter square is the area of the pipe. Proceed to the velocity. V equal to Z1 minus Z2. Z1 is 0.89, which is the height of the water jet, and Z2 is 0.64, which is the height of water supply. 0.89 minus 0.64, and divided by 2.2 second, which is the time taken, and velocity we got the 0.114 meter per second. For the flow rate, equation is velocity times with area. 0.114 the velocity and 0.201 is the area. We times that and we got 0.023 meter cube per second. And the data experiment for the result for the task 2A, we collect the data of the distance of connector from main supply and the time taken in the second. So the calculation for the task 2A, we calculate the data from hole 1 until hole 5. We calculate the flow rate with the equation of volume over time. We insert the value of volume is 0.25 times 10 power of negative 3 over 39.4 second, which is we got from the data table data. And the flow rate for the whole one is 0.006345 times 10 power of negative 3. And the velocity for the whole one, we use the equation of 4q over pi d squared. We insert the flow rate value to the equation. We got 4 times 0.006345 times 10 power of negative 3 divided by pi times with 0.003 square, which is the 0.003 is the diameter of the pipe, and we got the value of velocity is 0.897. And for the following hole 2, 3, 4 and 5, we just insert the data from the table above. And next, for the data and experiment result for the task 2B, we'll collect the data of the distance of connector from supply and the time taken in second. So, same as the task 2A, we calculate the flow rate with the equation of volume over time, and the velocity is the equation of 4q divided by pi d square. So we just insert the value of the insert the value of the time, which is in the equation of flow rate, which is 0.25 times 10 power of negative 3 divided by 36.5 second. We got the flow rate is 0.006849 times 10 power of negative 3. That's the flow rate for the whole one. And the velocity, we just insert the value of the flow rate in the equation. We got 4 times 0.006849 times 10 power of negative 3 divided by pi times 0.003 power of 2. We got the 0.968 meter per second. So it's the same for the connectors 2, 3, 4, 5 until 10. Just insert the data we got from the table result. Okay, next for the discussion of this experiment. Relating to Bernoulli's equation, the Bernoulli's equation is a fundamental principle in fluid mechanics that describes the conservation of energy in a fluid flow. It states that the total energy of the fluid remains constant along a streamline, comprising of kinetic energy, potential energy, and pressure energy. Flow rate experiments using open and closed loop hose pipes are closely related to the principles of Bernoulli's equation. For the open loop experiment and Bernoulli's equation, in an open loop hose pipe experiment, the Bernoulli's equation can be applied to different sections of the pipe to analyze the pressure of the distribution. The equation states that the sum of the kinetic energy, potential energy and pressure energy at one section is equal to the sum of at another section. By measuring the flow rate and pressure at different points, researchers can validate the energy conservation principle and gain insights into fluid behavior in open system. And the for the closed loop experiment and Bernoulli's equation in a closed loop hose pipe experiment, the Bernoulli's equation helps explain the pressure variation as the fluid moves through different elevations. As the fluid gains or loses elevation, there is a corresponding change in pressure. By applying the Bernoulli equation to different points along the loop, researchers can quantify the pressure variations and understand the energy changes within the system. So, for the conclusion of this experiment, in conclusion, flow rate experiment utilizing open loop and closed loop hose pipes coupled with an application of Bernoulli's equation offer a comprehensive understanding of fluid dynamics and practical implication. This experiment enabled researchers to investigate the relationships between flow rate, pressure, and elevation, contributing to the advancement of fluid mechanics and facilitating the design of efficient fluid system in diverse fields.